Hello, my name is Noson Yanofsky. We're in Discrete Structures, the class Discrete Structures. We're up to section 4.2, okay, which is about mathematical induction. Okay, so let me tell you what mathematical induction is all about. Mathematical induction is a way of proving statements. Okay, it's a way of proving statements. We want to prove statements about mathematics. We want to prove statements of the following form. For all n, this is true. For every single n, this is true. Some statement. Okay, now it's hard to prove something like that because that means it's true for n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, all n. All n means a billion, trillion, billion n, whatever. So it's very hard to prove such statements. What we're going to do is we're going to show a method of proving things and show how you prove something for every single n with just a two-step process. So it's very helpful. So I got to start off with a story, okay? And the story is a famous story. It's slightly even true. So there was a great mathematician. His name was Carl Friedrich Emanuel Gauss. He lived in the 1850s, 1860s, maybe a little earlier. But as a boy, he wasn't behaving well in school. So he was a 5-year-old boy. He was rambunctious, as they say. So he wasn't behaving. So they sent him here and they sent him there. And finally, the teacher had enough with him and wanted to keep him busy. So the teacher told him, "Hey, Mr. Gauss, add up all the numbers from 1 to 10. So he jumped up and he said 55, like this. So the teacher thought he was, misbehaving or just, not doing it. So she kicked him out of the office. He kicked him, whatever the teacher, probably a male teacher at the time, kicked him out of class. Okay. Next day he came in and he wasn't behaving again. Oh, that night he went home, added up all the numbers from 1 to 10, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, and found the answer was 55. Next day he wasn't behaving well. Okay, and the teacher thought maybe, like he knew this fact that the sum of numbers from 1 to 10 is 55, but he doesn't know it for all numbers. So the teacher asked him to add up all the numbers from 1 to 100. And without blinking an eye, he jumped up and said 5,050. Okay, so again, the teacher thought he was making a fool, making a joke, so kicked him out. That night the teacher went home. It was a long night, added up all the numbers from 1 to 100. 1 plus 2 plus 3 plus 4, all the way to 97 plus 98 plus 99, 100. The next day, the teacher thought, you know what, he knows 10, he knows 100. This 5-year-old kid knows 10. I'm going to pick a strange number. So the teacher says to him, add up all those numbers from 1 to, 362. Without blinking an eye, the 5-year-old gave an answer. And of course, the student went home, the teacher went home, and it was a long weekend, and it all added up all the numbers from 1 to 362, and he found out the exact answer that he gave. Okay? So I'd like to show you this little 5-year-old's trick of how did he do this. By the way, I put the board a little bit on the side because we're going to do a lot of writing today, and it's all equations and things like that, so we're going to have to be very careful about this. So here's the way he did it. Let's do from 1 to 100. Okay, and the idea is as follows. Usually, most people would add this as follows. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is 28, and keep on adding, etc., until you get to plus 96, plus 97, plus 98, plus 99, plus 100. But Gauss was a very smart boy, and he knew. Not only did he know this, which you probably knew or understood also when you were 5 years old, but he really understood what it means deeply. And what it means deeply is that it doesn't matter how you add numbers. It doesn't matter in what order you add numbers. So rather than doing it the way I would do it or the way you would do it, 1 plus 2 plus 3 plus 4, He added it like this. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. 4 plus 97 is 101. Dot, 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 dot. Okay? Now ask yourself, how many, each time I'm adding 100, I'm adding 101. Each pair is 101. How many pairs are there? And the answer is, well, I have 100 numbers altogether, so I have 100 over 2 pairs, okay? And each one of them adds 101. So you multiply that, 100 over 2 times, and so that's 50, 50 times, that's 50, 50, 5,050, okay? It's a very clever little trick, okay? Rather than adding them in order, just separate them by pairs and do that. Okay, so, by the way, let's erase this. Hold on, let's erase this, don't move. Okay. Let's do this for a general number n. 1 plus 2 plus 3 plus 4 plus dot 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 plus n minus 3 plus n minus 2 plus n minus 1 plus n. Okay, we're going to add them together. 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. Dot, dot, dot. So, how many pairs do we have? And the answer is n over 2. Okay, how much does each pair give? N plus 1. Okay, so now we can make a theorem. Okay, so that works out very nice. Okay, and the theorem says as follows. The sum of I equal 1 to n of I, adding up all the numbers from 1 to n, is equal to n, I'm just going to rewrite this, I'm going to rewrite it in a nice way, times n plus 1 divided by 2. Okay? I just want to point out, if either n is even or n plus 1 is even, one of them, exclusive or, one of them is even, so if one of them, since one of them is even, you can always divide by 2. This will always be a whole number. Okay, so that's very, very nice. Great. I'm just going to shut this light because it's not contributing to anything. Okay, so that is a nice theorem of Mr. Gauss. Okay. I just want to say, from the computer point of view, this is a very nice theorem. Because why? You're going to learn about this in analysis of algorithms. Look what it says. It says instead of adding n numbers, doing n additions, you can do one multiplication, one addition, well that's a simple addition, adding by 1, and one division, and you can do, instead of n multiplications, you can do 1, 1, and 1 of these operations, and you got the whole thing. Obviously, that's a lot more efficient than doing n additions. Okay? So you'll see a lot more of that when you take analysis of algorithms. Okay, so that's an interesting point. Okay, but now I want to prove this statement. Okay, now I gave you the intuition. The intuition should fit in perfectly. You now know that this is true. You can, not only can you know that it's true, by the way, it's a great little parlor trick. You can do it, you know, hey, ask me to add up, give me any number, I'll add up all the numbers from 1 to that thing. And if you practice this a lot, okay, you really, I mean, dividing by 2 is pretty easy. It's just one multiplication. If you learn how to practice doing that quickly, you can really do it nicely. But I don't want to do that. What I want to do is I want to prove it by mathematical induction. So what I'm going to do is I'm going to show mathematical induction and then explain how it works. Okay, so let's do it. So mathematical induction is 2 steps. One is called the base case. So here's the theorem. Okay, but I want to prove it using mathematical induction, and it's a two-step proof. Okay, base case. It is true for n equals 1. Okay, I want to show that it's true for n is equal to 1. So watch what it says for n is equal to 1. For I equal 1 to 1 of I, question, is that equal to 1? I'm setting n is equal to 1. This is 1 plus 1 divided by 2. Okay, so let's see what this is. This is 1 times 2 over 2. Question, this side, adding up all the numbers from 1 to 1 is 1. This side, 2 over 1 is 1. So yes, it's true. Is it true for n is equal to 1? Question mark. Answer, yes it is. We showed it's true for n is equal to 1. That's the easy case. Okay? Now, the hard case. Okay? The hard part is called, I call it the inductive case. Inductive case. Okay? And it says as follows. Assume the theorem is true for n is equal to k. N is equal to k. Now, what's k? I don't care. You'll see why we use k in a second. Assume the theorem is true for n is equal to k. Let's just, what does that mean? Okay, what that means is that the sum of I equal 1 to k, just writing this theorem, instead of using n, I'm using k, of I should equal to, let's plug in k times k plus 1 divided by 2. Okay, that's what it means. Okay, this is the inductive case, this is the base case. This is the inductive case. We have to assume this, and then we want to do the following. To show, sorry, I'm going to run out of room, so let's do this over here. To show the theorem is true for n is equal to k plus 1. Okay, so this is that second. This is the hard part. Okay, okay. We saw it's true for n is equal to. We saw it's true for n is equal to. We assume it's true for n is equal to. We assume it's true for n is equal to k. We want to show it's true for n is equal to k plus 1. What does it mean to be true for n is equal to k plus 1? Well, I'm going to, that is, I'm going to plug in k plus 1 over here. So here's what the statement looks like for n is equal to k plus 1. I equals 1 to k plus 1 of I. Okay, should equal to k plus 1 times k plus 1 plus 1. K plus 1 plus 1 is k plus 2 divided by 2. Okay? Just for the hell of it, because it's a little bit ugly here, I'm going to work this out to see what it is. But again, I didn't do anything yet. I'm just assuming this, and I'm showing what I want to do. To show. That's what I want to do eventually. So what I want to do is, eventually, and I will do it, but I want to do it here. I just want to show that this is equal. Well, let's just make sure that we multiply this out. This is k squared plus 2k plus 1k is 3k plus 2 divided by 2. Okay, so this is what I want to show. I want to show that if you add up all the numbers from 1 to k plus 1, you can get this. Okay, so again, the first step is easy. The second step, you have to split the second step into two parts, actually 3 parts. First part, show what you're assuming. Second part, show what you want to get. Third part, actually do it. Okay, and that's what we're going to do right now. We're going to actually go and show this. So let's write it out. Okay, and the whole class is just doing examples like this, and it's all the same format. So you just have to get the format and understand it. Okay? So the sum of I equal 1 to k plus 1. I want to prove that this is true. I have no idea that it's true. Somebody gave me this theorem. I have no idea it's true, but we're going to do it. Of I is equal to, okay? Now, rather than, I have no idea what it's equal to. I have absolutely no idea what it's equal to. Okay? So I can't write that it's equal to this. This is what I want to get. This is my cheat sheet. This is my cheat sheet. I want to get to here. Okay. Now, what I'm going to think of this is the new. I don't know what I is equal to 1 to k plus 1 is. I have no idea what it is. But you know what? I made a certain assumption here. I'd like to use that assumption. This is what we're going to do. So this is the new thing, and I want to use my old idea that I had, and I want to build the new. Okay? So I'm going to write it like this. I equals 1 to k of I. Okay, and this is the old. Great. Now, question. Is this equal to this? No, it's not equal to this. Okay? Look at this. Here I'm adding up all the numbers from 1 to k plus 1. Here I'm adding up all the numbers from 1 to k. So this is more than this. Something's missing here. What's missing? Well, you added up all the numbers from 1 to k. You really want to go till k plus 1. Well, manually add it in. Okay? I'm going to call this the fix. Okay? So basically, the new is equal to the old, but not really equal to the old. You still have to fix it. So I fixed it. Okay? Now, this is true. Doesn't help you much, but this is true. Adding up all the numbers from 1 to k plus 1 is the same thing as adding up all the numbers from 1 to k, and then adding the k plus 1 number. It's like if I have a room full of students, I want to add up everyone's age. Okay, one way is to add up everyone's age. Okay, another way is add up everyone's age till the last person, then add up the last person. Doesn't hurt. Okay, but now here's what I can do, and this is the part about induction. I assume something is true about here. So I'm going to use that assumption. So, what did we assume this is equal to? We assume this is equal to k times k plus 1 divided by 2 plus k plus 1. Okay? We assumed this part. We assume that this is equal to this. Okay? So now I want to see what this is equal to. Well, let's multiply it out and add it together. Okay, so let's do this. This becomes k squared plus k squared plus k, divided by 2, plus, I want to use this 2 over here, so I'm going to multiply the top and the bottom by 2, plus 2k plus 2. Oops. Really running out of room, but I need the room. So let's rewrite that a little bit smaller. So let's do this again. This is k squared plus k over 2 plus, now I want to add these. This is a fraction. I'm missing a 2 on the bottom, so I'm going to multiply the bottom by 2. I'm going to multiply the top by 2. 2k plus 2. Okay. Now add these together, you get k squared plus k plus 2k is 3k plus 2 divided by 2. Now, lo and behold, thank God I have a cheat sheet. We love cheat sheets. That's exactly what I wanted to show. That is exactly what I wanted to show. Okay? I wanted to show that the sum of all these things, is equal to this. That's what I wanted to show. And I did it. And the only thing I did was assume this was true. Okay. So that's the first example. Sorry, let's focus in a little bit on that. Okay, let's back up. Okay, good. Okay, now I want to go through it again, then I want to give you what the philosophy is. Okay? We want to prove this theorem using mathematical induction. Okay, I gave you the intuition of how it works by Gauss's formula, Gauss's trick, but here I want to prove it, and we're going to do that in a second. Okay, so first thing is prove it for 1. Second thing is assume it's true for n is equal to k. Then you want to show that it's true for n is equal to k plus 1. Okay, now you write down what you want at the end. That's what this is all about. Okay, and then what you do is you write down what you want to get by looking at the old, by the new, okay, and write the new in terms of the old, but you have to fix it. Since you're using this old, this k story, so then get it, write down what your assumption was. That's exactly what you assumed, plus add in the fix. Do a lot of math, and you get it. Okay, but now I want to give you the idea. The idea is as follows. I want to prove something is true for all n. For every single n, this is true. Whether you're adding up from 1 to 10, from 1 to 100, from 1 to 362, from 1 to 3,724, to etc., etc. Okay, so you want to get that mathematical induction. So here's what you do. Here's the way to think of the numbers. Think of the numbers as a long dominoes. Okay, an infinite string of dominoes standing up. Now, question. I want to prove this true for every single domino. I want to prove it true for, I want to knock down every domino. I want to say it's true for 1. I want to say it's true for 2. I want to say it's true for 3. I want to say it's true for 4. I want to say it's true for 16 billion. ... So here's what I do. Think of the dominoes. Let's say I wanted to knock down an infinite long list of dominoes. What do I have to do? Well, there's 2 things you have to do. One is knock down the first domino. Show that it's true for the first domino. Second thing, you have to show that every domino is close enough to the next domino. What does that mean? Every domino, if I knock this one off, down, then the next one will be down. Now, if you can show that's true, then it's true for every single domino, and the infinite set of dominoes will all knock down. That's exactly what we're doing here. I am showing it's true. I am knocking down the first domino, okay? And then I'm saying, if I can knock down the kth domino, if it's true for the kth domino, then guess what? Because it knocked down the kth domino, it's going to be true for the k plus 1th domino. That's exactly what we did. I now knocked down an infinite set of dominoes. Okay. Let me just, so that's one way of thinking of it. Again, we're going to do 7 examples of just this thing over and over. So, but I want to get the idea behind it correct. And the idea is as follows. The idea is as follows. You want to say it's true for 1. Okay? Now, you also have the following. If it's true for k, then it's true for k plus 1. What's k? Well, here I want to say k is 1. So, what did we say? If it's true for 1, then it's true for 2. Very nice. Now let's use logic. This we call modus ponens. If you know that p of 1 is true, and you know that p of 1 implies p of 2 is true, what do you know? You know that p of 2 is true. Great. Now, I showed that p of k, implies p of k plus 1. And you asked, what's k? And I'm saying it can be anything, including k, it could be 2. So this would be p of 2 is true. That means p of 3 is true. Now, modus ponens again. You know p of 2 is true, and you know p of 2 implies p of 3, then you know p of 3 is true. Great. Now, you know this is true for any k, including p is equal to 3. K is equal to 3, so you get p of 3, arrow p of 4. What do you know from that? Answer, p of 4. Okay? ... This goes on forever. So basically it's the following statement. If you know p of 1 is true, this you have to know is true, and you know that the truth of p of k implies the truth of p of k plus 1, then you know p of n is true for all n. Okay, so if you know this and you know this, if you know this is true and you know this implies this, then this whole statement is true for every single line. Okay, it's a beautiful idea. Okay, it's a beautiful way of proving things, and it works in so many different ways. Okay, so let's do some more examples of it. We're going to start off doing easy examples, then we're going to build up to harder and harder examples, but none of it is very hard. Okay, so here's another theorem. We did this in class, the first week of class. It says as follows: if S equals n, if the number of elements in a set is n, then the number of elements in the power set of S is equal to 2 to the n. Okay. Okay, so we want to prove this. This is a theorem. So we're going to prove by mathematical induction. It's the only types of proofs we're going to do today. Okay, and it goes as follows. What does it mean that? Let's try it. We're going to prove it for n is equal to 1. So this is the base case. Sorry, I have to write the base case. Proof. Base case. Okay. S is equal to 1. Now, what does it mean, a one-element set? Well, that means S is equal to, I don't know, maybe it has that element. It could have the set, it could have the element X, it could have the element Y, I don't care. But the power set of S, what's the power set of S in this case? It's the empty set and the set containing A. The only subsets of this set is the empty set. The empty set's a subset of everything, and itself. That's it. That's the only thing. Okay. Well, in that case, the number of elements in that set is 2. I'm going to write 2 a funny way. I'm going to write 2 as 2 to the 1. Okay. And so it's true. Okay, because I set n is equal to 1, so 2 to the 1. You have 2 to the 1. It works. Okay, great. That's the base case. Induction. Okay. Assume. You have to always assume something in an induction case. Assume that if S is equal to K, I'm stating the same theorem, but about K now. Then the power set of S is equal to K. 2 to the K. Okay. It's a simple assumption. Okay, great. To show if the power set of S, I'm going to write a different S here. Because, why am I going to write a different S? Because here I'm talking about the set S. So let's talk about a set S prime. If the set S prime is equal to K plus 1, comma, then the power set of S prime, okay, that's a different set than that, is 2 to the K plus 1. Okay, that takes care of that. So this is what we're assuming, and this is what we're showing. Now, we did it in class. We saw that a one-element set has 2 subsets. A 2-element set has 4 subsets. A 3-element set has 8 subsets. A 4-element set has 16 subsets. We did those examples in class, but we want to show it in general. Okay, so let's show it. Okay, so let's show it. Okay, so we're going to let S is equal to the set A1, comma A2, comma comma AK. S has those elements. Great. Okay. Now, but we're not interested in SK. K, what are we interested in S with K elements? We're interested in this set. S prime, which has A1, A2, A3, all the way to AK, and then A to the K plus 1. It's just subscripts, just means different numbers. So S has these elements, S prime has these elements. Great. Now, what I'd like to do is, I'd like to go back to what we did in class and show what happens when you add one more element to your set. That's exactly what we're doing. We're showing what happens when you add one more element to your set. I'm sorry, I don't have a lot of room here, so I'm going to erase. You have to take notes. We're going to do it. Okay? So let's just go through what happens. Okay? So let's take the power set of A comma B. It's a two-element set. Let's see what we got. We get the empty set, the set containing A, the set containing B, the set containing A comma B. That's four-element set. Great. Now I want to look at what happens when I have a third element. So this is a two-element. I want to see what happens when we get a third element. Again, I'm going up one because that's exactly what we did. We went from K to K plus 1. Okay, so let's do this. The power set of A comma B comma C. Okay, let's do it. Okay, that's the empty set is there. The set containing A is there. The set containing B is there. The set containing AB is there. Okay, stop. So far, it's exactly the same set. But now, we have a new element C. So I want to show you what happens with this new element C. Well, basically, this element C could be part of this set. So that would be, what would that set? I'm doing it in different colors just to show you this, but it's the same thing. So this would be the set C. The set, I'm going to add in that C over here. I'm going to get A comma C. I'm going to add in that C over here. I'm going to get B comma C. I'm going to add in the C over here. I'm going to get A, B, C. Close it off. Okay, notice what happens. Here I had 4 elements. Here I have 1, 2, 3, 4, 5, 6, 7, 8 elements. Great. Guess what I'm going to do now? You guessed it. Okay, I'm going to do A, B, C, D, just to get a feel for it. Power set of A, B, C, D. Okay, well, guess what? The empty set, the set containing A, the set containing B, the set containing AB, the set containing C, the set containing AC, the set containing BC, the set containing ABC, comma, don't move. What else? Well, I just listed off all the subsets that do not contain D. But guess what? There are subsets that do contain D. So look what I do. I add in D to every one of these subsets. Because look, a subset of this set can either contain D or not contain D. This is the ones that do not contain D. Let me show you the ones that do contain D. I add in D over here. 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 A, B, D. Okay? I add in C, D. I add in A, C, D. I add in B, C, D. And I add in A, B, C, D. And now I had 8 over here. I have 8 more over here. I have 16. Okay? Great. Okay? So what did we just see? We saw when you go from 2 to 3, you double the amount that you had over here. When you go in from 3 to 4, you double the amount. Okay? And for any n, when you go from k to k plus 1, you are going to double the amount. Okay, so watch what we're going to say it over here. So let's do it the same way we did this. You ready? The power set of S prime is going to equal to the power set of S. Okay, it's going to have all those old ones in blue, union I don't know how to write it. All the subsets with, when you don't know how to write something, you write it in English. All the subsets with A of k plus 1 added in. That's exactly what I just did. I added in all the new things. Okay, the new thing. So again, I had from 1 to k over here. Now I have from 1 to k and k plus 1. Okay, great. So how much is that? Well, the number of elements in here, which is, by the way, what we're looking for, the number of elements in S prime, is equal to the number of elements in S plus the number of, like that, okay, which is equal to the power set of S. Damn, hold on. Okay, you know what? We'll write it like that. The power set of S plus the power set of S. Okay? Because the same amount of elements in here is in there. Okay? So how many elements are in here? The power set of S. How many elements are in here? The power set of S. So we can write this as 2 times the power set of S. Hold on. How many elements does the power set of S have? Answer, we had an assumption about that. So this is equal to 2 times, that's our assumption, 2 to the k. Great. So how many elements does the power set of S prime have? Answer, 2 times 2 to the k, which is 2 to the k plus 1, which is exactly what we wanted to show. That's our cheat sheet. It matches up. What we wanted to show and what we showed is equal. So it works. Let's just go through this again. We assumed that the power set of S is 2 to the k. We wanted to show that the power set of S prime, which has one more element, is 2 to the k plus 1. And what we did was we looked at the new power set, okay, and we saw that every time we add one letter, we're always doubling what was previous. So here was 4, here's 8, 2 times 4 is 8, 2 times 8 is 16, and it would go on the same way. So that's exactly what we showed here. The power set of S prime is the power set of S. It's basically, the size is 2 copies of the power set of S. Power set of S and all the subsets with A of sub k plus 1 added in. Okay, so that's power set of S plus power set of S, which is 2 times the power set of S, which is 2 times, by assumption, we said the power set of S is 2 to the k, so we have, so that's 2 times 2 to the k, which is 2 to the k plus 1, which is what we wanted to show. Okay, straightforward and not hard. Let's do a little bit of a harder one. I hope this is understandable. I hope this is viewable. I just want to focus on the bottom over there. Okay, make sure you saw that. Okay, great. That light bothers me. Okay. Let's do another one. Sorry, we're a little bit out of room. Okay, let's do the next one. Okay, this is an exercise from the book. We're doing it here. I think at the end I do most of the book's exercises, and then you get homeworks, the other ones. So let's do this. Theorem goes as follows. 4 plus 10 plus 16 plus dot 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 plus 6n minus 2. I have to figure that out. Okay. So you take 4, add 6 to it, you get 10. Add 6 to it, you get 16. Add 6 to it, you get whatever. You're going to get 22. Okay. Add 6 to it, you're going to get 22 plus 6 is 28. Okay. 28 is 6 times 5 minus 2, let's say. Okay. This should equal to, here's a secret formula, just like Gauss had a secret formula, here's a secret formula, 3n plus 1. Okay, now I just have to tell you, I promise you, on the test and the midterm, there will, on the test and the next, on the quiz and in the final, there will be such a mathematical induction. Promise you. Okay, but one thing, I will not ask you to come up with these secret formulas. I'll come up with the secret formulas, you have to prove them. Okay? And how do you prove them? Mathematical induction. Okay? Let's just write this the way it's written usually. It goes as follows. The sum of I equal 1 to n of 6i minus 2. Okay? Instead of starting off at 6, you start off at 4. Instead of the second one, instead of being 12, you start off at 10. Okay? That's equal to n times 3n plus 1. Okay, let's do the basic case. I'm sorry, it's not called the basic case, it's called the base case. The bottom, the base case. Because it's the first thing you do. Okay, it's the first part of it. Okay, let's put this away because it's confusing me. Okay, and let's actually run it. Okay, so we're going to start it, set, show, not show, we're going to actually do. Okay, the base case is, it is true for n is equal to 1. So let's do it. The sum of I equal 1 to 1 of 6i minus 2. Okay, what's that equal to? Well, you're just going to do 1. So this is equal to 6 times 1 is 6 minus 1. That should be 4. Question, is that equal to, let's do this, 1 times 3 times 1 plus 1. 3 times 1 is 3 plus 1 is 4. Okay, so this is equal to 1 times 4, which is equal to 4. It works. It's true. 4 is equal to 4. Yes, it is. We asked, is it true? And so it showed that it is. Okay, great. Now let's do the inductive case. Okay, the inductive case. Assume the sum of I equal 1 to k, show it's true of k, of 6 to the I minus 2 is equal to, I'm plugging in k here, k times 3 times k plus 1. So we're going to assume this is true for k. Great. To show, this is what we want to show. This is our cheat sheet. We write our cheat sheet before we even get busy trying to do it. We're to show the sum of I equal 1 to k plus 1. And we're going one step higher, of 6i minus 2 is equal to k plus 1. I'm plugging k plus 1 into n. Every time I see an n, I'm plugging k plus 1. Okay, times 3 times k plus 1 plus 1. Okay, now this is what we want to show just to make our cheat sheet. You know, when you cheat on a test in Brooklyn College, you make sure that the paper is a small paper. So I want to get what I want to get to. I want to get the cheat sheet to be as small, compact as possible. So let's multiply this out. This becomes k plus 1 times 3k plus 3 plus 3k plus 3 plus 1 is plus 4. Okay? So we got that summed into one thing. 1 second. Let's multiply this out because, again, we want to make it compact as possible. So this becomes FOIL 3k squared plus 4k plus 3k is plus 7k plus 4. Okay, this is what we want to show. Great, we got our cheat sheet set up. Good. We know what we want to show. Okay, I'm going to erase this over here. Just I need a lot of room over here. So we're going to do it. Okay, great. Now that we know what we want to show, it's easy to actually do the calculations. So let's write it out. The sum of, what do we want to show? We want to show from I is equal to 1 to k plus 1, okay, of 6I minus 2. Okay, now, this is the new. I want to do this for the new. I'm going to write the new in terms of the old. I made an assumption here about this guy, so I'm going to use that assumption. This new is equal to the sum of I equal 1 to k of 6I minus 2. 1 second, that's not equal. This is the old. That's not equal, okay? Because this only goes from the new to the, this only goes, I'm sorry, this goes from 1 to k plus 1, this goes from 1 to k. You're missing something. So we better add it in. Okay, so we're going to add it in. Okay, so stop the computer for a second. Write down what we're adding in, because this is a key point. What are you adding in? You're not adding in anything with an I. What you're adding in is as follows. You're adding in, shoot, I'm running out of room. 6k plus 1, 6 times k plus 1 minus 2. Okay, 6 times k plus 1 minus 2. That's the k plus 1th term there. Okay, so this was the fix. The new is equal to the old plus the fix. Okay, now let's work it out. Hey, I have an assumption about the old. I have made an assumption about the old, so let's write it out. So this is equal to, what's my assumption about the old? That this is equal to k times 3, right over there, 3 times k plus 1. Okay, that's my assumption. Plus, don't forget your fix. This is 6k plus 1 minus 2. Okay, let's work this out. We're going to get k times 3k is 3k squared plus k plus 6k plus k plus 6k is plus 7k. Okay, hold on. This we finished. Now we have this. 6 times 1 is 6 minus 2. 6 times 1 is 6 minus 2 is plus 4. Holy cow. Batman, I think we got it. We got it. Okay, so that is a very cool. This is what we wanted to show. We used the assumption. We got it. Okay, let's do another example. Again, there's nothing hard here. The main hard thing, not the main, the main idea, I just set up the problem here. Okay, obviously this wasn't set up, this had to work. What I wanted to assume, what I wanted to show, I'm sorry, what I assumed, what I wanted to show, and here I actually did what I had to show. I wrote this, but I wrote the new in terms of the old. The new in terms of the old. And then the rest is just a little bit of math. Okay, let me just make sure that this is viewable. Okay. Go back and forth with this. Okay, so that works out very nice. Okay, let's do another example. theorem. Okay. N factorial is greater than 2 to the n. Okay. Let me first give you an intuition of why this is true. Okay. Let me give you an intuition of why this is true. Okay, and then we'll actually prove it using mathematical induction. So what's n factorial? N factorial is n times n minus 1 times n minus 2 times n minus 3 times dot 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 times times 3 times 2 times 1. Okay, great. What's 2 to the n? Well, it's 2 times 2 times 2 times 2 dot 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 times 2 times 2 times 2. Okay? Okay. Now, what you can see is most of the time n is larger than 2. Okay? All these numbers are larger than 2. So you're multiplying the same amount of numbers, 2, 2, 2, 2, n numbers, okay? These are only 2's, and these, that's 2 to the n, and these are most of the time larger, except over here, this is not larger than this. Okay, we'll see about that in a second. Okay, so that's the intuition. The intuition is, of course, this is larger because you're multiplying larger numbers than this. Okay, but I don't want to do it with intuition, I want to do it with mathematical induction. So what I'm going to do is I'm going to erase this. Okay, and we're going to do the base case. You know what? Base case is so easy, we're not going to do the base case. Okay, we're going to do the inductive case. Okay, assume. You know, we assume for k factorial is greater than 2 to the k. Okay, I just plugged in k instead of n. I plugged in k into n to show k plus 1 factorial is greater than 2 to the k plus 1. Okay, that's my inductive step. I don't know a better way of getting it. Okay, so let's look for a second at what k plus 1 factorial looks like. Okay, so that's it. I finished. I told you what I'm assuming, I told you what I want to show, and now we have to actually do it. So what's k plus 1 factorial? Now, again, my goal in life is always to write the new in terms of the old. So this is the new, this is the k plus 1. I want to write it in terms of the old. Well, that's the old. So let's do that. That's equal to k plus 1 times k factorial. Let's just make sure we understand what that means. What's k plus 1 factorial? It's k plus 1 times k minus 1. What's 7 factorial? It's 7 times 6 times 5 times 4 times 3 times 2 times 1. What's another way of saying this? Well, it's 7 times, what the hell is this? 6 factorial. Okay? So k plus 1 factorial is just k factorial with a new thing there. Hold on, don't move. This is the old. Okay, so what do we know about that? What did we assume about this? And the answer is we assume that this is greater than, I'm just going to write this thing, because it's k plus 1, is times, what did we assume this? This is times 2 to the k. Okay, that's our assumption. Okay, hold on. K plus 1, what's k plus 1? Well, let's just, I don't know. By the way, what's k? I have no idea. But let's assume k is more than 1. Okay? If k is more than 1, then k plus 1 is more than 2. So then this, k plus 1 is more than 2. Okay? So k plus 1 is more than 2, then if k plus 1, if k is more than 1, k plus 1 is more than 2. So this becomes 2 times 2 to the k. Okay, 2 times 2 to the k is equal to 2 to the k plus 1. I did it, that's right there. So I showed that k plus 1 factorial is greater than 2 to the k plus 1. I twisted one thing here. Okay? The whole time, every time I mentioned k, I said, what's k? K can be anything. But here, notice what I said. I said k has to be more than 1. Okay? Oh, that's an interesting thing. We have a new thing. K is more than 1. Okay, great. So we proved it. Now, let's just test it for a second. 2 factorial is greater than 2 squared. Let's see if that's true. 2 factorial is 2. 2 is greater than 4. Buzz. That's not true. Okay, it's not true. By the way, how about 1 factorial? 1 factorial is 1. Is that greater than 1 squared? 1 is greater than 1. 1 squared is 1. No, that's not true either. So that's not true either. Great. So we proved the theorem, but it's not true for 1 and it's not true for 2. By the way, that was our base case that we didn't write. We should have done it in our base case. Okay? But I didn't do it in our base case. You know why? Because it's false for 1. It's even false for 2. Let's look about 3. 3 factorial is greater than 2 to the third. Let's see. 3 factorial is 6. Is 6 greater than 8? Buzz. No, it's not. It is not bigger than 8. Okay? Let's try it for 4. 4 factorial is 4 times 3 is 12, times 2 is 24. His question, is that greater than 2 to the 4th? What's 2 to the 4th? 16. Is 24 bigger than 16? Yes, it is. Okay? Okay. So, lucky I didn't do the base case, because if I would have done the base case, I would have seen it's not true, and we needed for both things to be true. We needed this to be true. Okay? And the answer is it's not true for 1, it's not true for 2, it's not true for 3. In fact, this statement is not true. Okay? It's true for all n greater than 4, greater than or equal to 4. It works for 4. It works for 5. How do you know it works for 5? Well, if k is equal to 5, then it's true for k plus 1. It's true for 6. How do you know it's true for 7? Well, if k is true for 6, then it's true for 7. If it's don't keep on doing it. Okay, let's go back to our analogy with our infinite set of dominoes. Let's say you have an infinite set of dominoes, and you prove that every single domino is connected. If you knock down the kth domino, it's close enough to the k plus 1th domino, and it will knock it down. So every single k knocks down the k plus 1. But let's say you cannot knock down the first domino. Let's say somebody put crazy glue there. You can't knock down the first domino. You can't knock down the second domino. You cannot knock down the third domino. You can knock down the fourth domino. Okay? Well, if you can knock down the fourth domino, you've knocked down all of them. Okay? So let's just go through what's the problem here. The problem is exactly what I showed before. Okay? Let's do 3. 3 factorial is 3 times 2 times 1. Okay? 2 to the n, 2 to the third is... So yes, this number is bigger than this. This number is the same as this. This number is smaller than this. But if you multiply these out, you'll get a smaller number than if you multiply these out. Okay? So even though this is bigger than this and this is the same as this, because this is lower than this number is not larger than this number. Okay, but here we had an interesting case because the base case is false for n equals 1, 2, and 3. True for n equals 4. Okay, so that's a very interesting thing. The base case, we couldn't have the base case down at the bottom. We had to push that up. Okay, so very nice. I skipped the base case on purpose. Okay, great. Let's do another example. Another example. Okay. It goes as follows. It's another induction, but here the math gets a little bit ugly. But we're here together. We're going to survive this crisis together. So let's do it together. Okay. The sum of I equals 1 to n. I'm sorry, I didn't write the word theorem. Theorem of 1 over 4i minus 3 times 4i plus 1 is equal to n divided by 4n plus 1. Okay? I have no idea how anybody ever thought of what these things are all about, how they came to this idea, but that's fine. We're going to do it. Okay, so we're going to do it. Okay, so let's do the base case. Let's hope it's true, the base case. Okay, so the base case says as follows. Well, we're going to do it n is equal to 1, so 1 over 4 times 1 minus 3 times 4 times 1 plus 1. Question, is that equal to 1 over, that's a question mark, question, is it equal to 4 times 1 plus 1? Let's do this. 4 times 1 is 4 minus 3. So this is equal to 1. 4 minus 3 is 1 times 4 times 1 plus 1 times 5. Okay, and this is equal to 1 over 4 times 1 is 4 plus 1 is 5. Anyways, yes, it is true. Okay, so they're both equal to 1 over 5. It's true. Very nice. Okay, great. Now, I'm going to need a lot of room, and this is a small board. So the base case is easy and obvious. We're going to do now the inductive case, but I want all the room that I possibly can get. Okay. I shouldn't have erased the theorem because now I can't remember it. Okay, so let's do inductive case. Okay, so we say as follows. Assume the sum of I equal 1 to k, we're doing it for n is equal to k, of 1 over 4i minus 3 times 4i plus 1 equals k, so I'm plugging in k in here, 4 times k plus 1. Okay, so that's what we're doing. Okay, to show the sum of I equal 1 to k plus 1 of 1 over 4i minus 3 times 4i plus 1, okay, is equal to k plus 1 divided by 4 times k plus 1 plus 1. Okay, hold on, this is our cheat sheet, so we better get it into a nice shape. Okay, so this becomes k plus 1 on the top, the numerator, 4k plus 4, so this becomes 4k plus 5. Okay, great. Now we simply write the old in terms of the new. Okay, so this is our cheat sheet. We're going to stop right there. Okay, and now we're actually going to do it. So we're going to do as follows. The sum of I equal 1 to k plus 1 of 1 over 4i minus 3 times 4i plus 1 equals the sum of I equal 1 to k of 1 over 4i minus 3 times 4i plus 1. Hold on, because that is not equal to this. This is the new in terms of the old, but we need the fix. So let's do the fix. Plus, what's missing here from here? And the answer is the last term, the final term, the k plus 1th term. So we get plus the final term. So what's the final term? 1 over, when you plug in I is equal to k plus 1. So let's plug it in. 4 k plus 1, this is why I moved the camera over so you can see, minus 3, did that right, times 4 k plus 1 plus 1. Okay, and this is the fix. Great. Okay, don't move. We had an assumption about this. So this is what we want to show, and we're writing the new in terms of the old. But one second, we had an assumption about the old. So let's write the assumption very clearly. So this is equal to, what did we assume this whole thing was equal to? We wrote it right here, so we don't forget it. So this is equal to k divided by 4k plus 1. By the way, that's much easier than this whole thing. Plus, don't forget the fix. But while we're writing the fix, I want to fix up the bottom. The numerator is a little bit messy there. So let's write it. So that's 1 over, let's see, 4k plus 4. 4k plus 4 minus 3 is 4k plus 4 minus 3 is plus 1 times, whoops, no, let's not do that, times, okay, let's do this, 4k plus 4 plus 1 is 4k plus 4 plus 4k plus 5. Okay, great. Now all we have to do is add these two things together, which is just arithmetic, and we already have a cheat sheet because we know what we want. Okay, but it's not easy. Okay, great. So this side has a 4k plus 1. This has a 4k plus 5. I need to get common denominators, so I better multiply this by 4k plus 1. Okay, and pray to God that I didn't make a mistake. So far so good. So, just to make it more educationally correct, let's multiply the bottom by 4k plus 5 so that I can add these two fractions. But one second, you can't just add it to the bottom, you got to do it to the top also. So let's multiply both the top and the bottom by 4k plus 1, 4k plus 5, and then the bottom also 4k plus 5. Okay, now let's unite everything and get it correctly. This whole thing is going to equal to, let's be careful here, okay, so we get 4k plus 5 oh, don't forget that. Stop. Okay, I tried to see if maybe we can fix it a little bit better, easier, but it's not going to go easier, but I got a new pen. So let's do this. So this becomes 4k squared plus 5k plus 1 divided by 4k plus 1 times 4k plus 5. Okay, that's good. Okay, basically, and now you look what you have. I'm sorry, you look what you have, you look what you want. That's the purpose of a cheat sheet. And you say, how can I get that? So the answer is very simple. Now factor that. So this becomes k plus 1 times what's missing. 4k plus 1. Let's just make sure that's right. K plus 4k is 4k squared. Plus 4k plus k is 5k. 1 times 1 is 1. So we got that. Divided by 4k plus 1 times 4k plus 5. This goes out without, and you're left with k plus 1 divided by 4k plus 5, which is exactly what you wanted. Which was exactly what you wanted. Okay, great. Great. One more. I'll call it a day. Okay. Again, I don't do any examples that the book does, so you're going to read the book on your own. Okay. I think we did 6 examples. We'll talk about this. Now, the next one is it's the same shape as the other ones, but it's a little bit different, but it's nice. Okay? And it goes as follows. Theorem 11 to the n minus 4 to the n is divisible by 7. Okay? So that's a theorem. I told you I will be giving you theorems. The hard part here is proving these theorems. Okay? So let's just see why this is a complicated thing, because 11 to the, let's say 11 to the 10th power, I have no idea what 11 to the 10th power is. It's a humongous number. Ugly number. 4 to the 10th power is a humongous ugly number, but somehow between them, if you subtract one from the other, it's divisible by 7. It's a statement. Okay? I'd like to show you why it's true. So let's do it for the base case. Base case. Okay? Base case is when n is equal to 1. So 11 to the 1 minus 4 to the 1. What's 11 to the 1 minus 4 to the 1? That's equal to 7. Is divisible by 7. Okay? We are finished. That's true. That's the simplest thing in the world. Okay? Great. Assume 11 to the k minus 4 to the k is divisible by 7. Great. To show, here's our cheat sheet, 11 to the k plus 1 minus 4 to the k plus 1 is divisible by 7. Okay, let's do it. Okay, that's our cheat sheet. Let's work it out. Let's do it. Okay, and the answer is as follows. 11 to the k plus 1 minus 4 to the k plus 1. This is the new. I'd like to write it in terms of the old. Is equal to 11 to the k minus 4 to the k. Now, that is definitely not true. That is just definitely not true. So this is the old. We need to fix it. Okay? And this is a little bit where it gets a little bit hairy. And again, the first time you see this, you wouldn't have thought of this yourself. I wouldn't have thought of this myself. But once you see it, you can understand it. Well, you know what? Is this equal to this? No, it's not. What's missing? Well, first thing is missing. This is 11 to the k plus 1. This is only 11 to the k. So let's multiply that by that. Okay, did that help? A little bit. Okay, I need to fix more. So let's multiply this out. Okay, so let's multiply this out. This is 11 times 11 to the k is 11 to the k plus 1. That's great. That's true. Okay, now, but I have, this is also equal to minus, this is equal to, hold on, don't move. Okay. Well, I have, this is 11 times minus 4 to the k. I don't have that. What I do have is, so let's get rid of that. Let's get rid of that. So by multiplying it by 11, I get 11 times minus 4 to the k. So add 11 times 4 to the k here. Okay, let's just work it out. Let's see what's that's equal to. So 11 to the k minus 1 minus 4 to the k. 11 times 11 to the k is 11 to the k plus 1. Good. Next, minus 11 times 4 to the k plus 11 times 4 to the k. That's going to cancel that out. This term plus this term is equal to 0. But that's still not equal to this, so we better multiply that out also. Okay, I'm going to write this a funny way. Minus, I'm just going to, this is my fix, right? This is my fix. Here's my fix. Okay, I wanted to get rid of this 11 times minus 4 to the k, so I added 11 times 4 to the k. But I'm still missing this thing, so we better add in that thing. But I'm going to write it a funny way. I'm going to write it as 4 times 4 times 4 to the k. Okay? Now, let's just work that out. Let's make sure it works. This is equal to 11 times 11 to the k, that we got, minus the 11 times 4k, plus 11 times 4 to the k, that's going to cancel out, minus 4 times 4 to the k is 4 to the k plus 1. Very good. Now, I'm just going to write this a funny way. I'm sorry, I'm just going to write, I wrote it like this because I wanted to write this a nice way. This is 11 minus 4 over here. So let's write this as follows. I'm going to write this as follows. 11 times 11 to the k minus 4 to the k. I'm just rewriting that. Close. Plus, I'm going to pull out the 4 to the k. 4 to the k. Pull it out. Factor it. 11 minus 4. 11 minus 4. By the way, what's 11 minus 4? That's 7. Okay, great. Fine. Now, that's it. I'm finished. Okay? Now, great. What do we know about this? I didn't use my assumption of this. This is divisible by 7. Okay. What does it mean divisible by 7? That means if I factored out all the numbers, there would be a 7 in there. Great. Now, if I factored out all the numbers here, there would be a 7 over here. And if I multiply by 11, there'd be a 7 over there too. So this whole thing is divisible by 7. Great. What else is divisible by 7? Well, if this is equal to 7, then this thing is divisible by 7. Okay, so you have something divisible by 7. The whole thing is divisible. Well, I'm sorry. We assumed this is divisible by 7, but by just about that is divisible by 7. That's also divisible by 7, because when you multiply something that's divisible by 7, it's still divisible by 7. Anything with a 7 in it is divisible by 7. Conclusion, add two things that are divisible by 7. Well, you can factor out the 7 out of them. That's divisible by 7. Conclusion, this whole thing is divisible by 7. If this number is divisible by 7, then this number is also divisible by 7. They're equal. Okay? So this was This was painful, but let's remember. We wanted to, the base case was easy. We wrote the assumption. This is what we want to prove. So we wrote the new in terms of the old. But we had to do a lot of juggling to fix the old by adding new things to get that. We fixed it, but when we fixed it, we saw what we were adding, we saw what we were doing, and we got it, and it's divisible by 7. Let's just show how it's divisible by 7. This we assumed is divisible by 7, right over there. Multiply it by 11, it's still divisible by 7. This is 11 minus 4, is multiplied by 7, is 7, so this whole thing is divisible by 7, is divisible by 7, is divisible by 7. Together, finished. Okay, great. Okay, so that's the end. I think we did 6 examples. We did 6 examples. Hold on. We did 6 examples. The book has at least another 5 examples that you're reading the book. Besides that, the last page of this booklet here, I gave you another example. This is an example I used to do in class, but it just took too much time and it was too heavy in the math. So what I did was I wrote it out very, very carefully with a fancy program called LaTeX, and it's the exact same thing, but you're going to have to read it on your own. This is the theorem we want to prove, the base case, okay, but the base case is here 2, not 1, because it's not true for 1, and then inductive. If k is true, then k plus 1 is true, so we assume p of k, and I show you what that means, and to show p of k plus 1, I show you what that means. Okay, I wrote a little a over here and a little b over there. You'll see why later. Okay, and then again, I wrote this, so we're doing it my way. We do it new in terms of the old plus a fix. Okay, and by assumption, I show you what I change the old into what we assumed, and the bottom line is just a lot of ugly math. Okay, and at the end, we get exactly what we wanted to get. The B's match up. Okay, so that's a very nice thing. Mathematical induction is a beautiful subject. It's a beautiful way of proving things. And once you get it, you're set for life because you'll know how to do it. Anyways, have a great day.